Welcome to our physics digital classroom, and today we are going to talk about collisions, or when things collide. So I'm really excited about this lesson because I think it's going to bring a lot of the things we were learning with momentum into perspective. So let's recap really quickly. Momentum is mass times velocity. We know that momentum relates to forces, which means it relates to accelerations, so it relates to how things move. Now, there's two different types of collisions. The first type is called elastic, and the second type is called inelastic. The basic ideas with these are as follows. Elastic collisions are where things hit and then they are separate and they go on. So the official definition right here is objects collide. So in an elastic collision, only conservative forces sorry about that, I'm not writing well today, and mechanical energy is conserved. When I say mechanical, that includes kinetic energy. Inelastic collisions are often when the objects that collide stick together. All right, and so an inelastic collision, they stick together. In a partially elastic collision, you have a little bit of both going on, and those are hardest to model. So in this class, we're going to focus on completely elastic collisions and then completely inelastic collisions, and we're going to kind of ignore the middle part. So here's the idea. In an elastic collision, energy is conserved. So the energy initially has to equal the energy afterwards. We're not losing any energy to friction or maybe heat or something like that. So what happens is, let's suppose we have an object and it is moving this way. We'll call it object 1, and it collides into object 2. Now, object 1 has some momentum, and object 2, we'll call this M1, V1, and P1. Object 2 has some initial momentum. Suppose it stopped. After the collision, after the elastic collision where they don't stick together, the following equations are true. I would challenge you, and this is probably one of the only opportunities you'll get for extra credit. If you can derive these equations, then I will give you some extra credit on the next exam. But for the rest of you, I'm just going to give you the equations. We spent about 3 weeks, maybe a week, last year in physics trying to prove these out, so they're quite complicated. So V1 final is the mass 1 minus mass 2 over mass 1 plus mass 2 times V1 initial. So after this collision, the final velocity of the first one is mass 1 minus mass 2 over mass 1 plus mass 2 times V1 naught. This should appear in your equation sheet. Again, this is for elastic collisions, and this marker is dying. Now, what's the velocity of the second one? Well, V2 final is 2m1 over m1 plus m2 times V1 initial. All right, and there are example problems which you'll go over for homework. So you should know these two equations for elastic collisions. Yes, they are quite challenging to derive. Yes, I will give extra credit if you can derive them. I'm out of black markers, oh no. But those are the equations. So you have something colliding into something else. These give you the velocity after that collision. Now, if the object's masses are the same, then you'll notice that the first one stops. So if you have two bumper cars with the exact same mass, and the first one runs into the second one, it doesn't depend on the second one's velocity at all. The first one will stop. All of that energy will transfer into the other one, and the second one will go much faster, okay? Now, moving on to inelastic, the picture is this. You have two objects coming in. Hopefully object 2 is moving slower than object 1. After the collision, they are attached. So you can imagine maybe two vehicles or two gliders with a magnet in between them. So after they hit, the magnet will attach them and they will continue. You could also think of maybe a really big truck hitting a really small car. The two will probably become an ugly mesh together and then keep going. An inelastic collision. So the equation for inelastic collision is actually pretty easy to derive. We take the momentum of the first one, add the momentum of the second one. In this case, energy is not conserved, but momentum is conserved. So we have the momentum of the first one plus the momentum of the second one, and that equals the momentum of the third one. The mass is mass 1 plus mass 2 because they're now 1. And then they have a new velocity. I'll call that 3. So you can solve this equation for any missing pieces. Now, when this is 0, it actually becomes a much easier equation to solve. Now, finally, we have pendulum that are included in your lesson. And those also follow the same characteristic. Now the last part of section 11b is pretty fun because it involves vectors, not to be confused with the student. His name is Victor. So, a collision in 3 or 2 dimensions. So suppose you have maybe an object here, and then an object hits it, and then this object then flies off that way. This object flies off this way. Well, momentum is still conserved. So what you're going to do is you're going to do sum of the momentum equals 0. And you'll do that in x and y, just like you did before. So let's assume that this guy is stopped. This guy's momentum is completely in the right direction, okay? So his momentum in x is m1v1, or hers. We don't discriminate here. Now, afterwards, it hits this one and they go off in different directions. The momentum of this guy or girl, object, there we go, plus the momentum of this object must equal this one. So this object will now have a momentum in that direction. I can simplify that down to an x and y using sines and cosines if I know that angle. And the same way, I can simplify this object's momentum in terms of x and y. And since I had 0 momentum in y, my final momentum in y must be 0. So if I take py from this object and add it to py of this object, they must equal 0. Since I did have an initial x momentum here, the two x momentums will equal this initial. And that is section 11b.